of this cosmology school. So today we're going to have the third lecture of Professor Pedro Ferreira. So we're going to learn about how to test modified gravity with observations at large scales. And just a couple of announcements. First, Pedro will not be able to participate in the Q&A session today. But I think during his last lecture, there will be time for more questions. And tomorrow we will participate in the Q&A also, but not on Friday. So without further ado, Pedro, please go ahead.
Okay, I'm going to share screen. Is that what I want? No, this is what I want. Share. Okay, and then I need to compact that. Very good. Can you see it?
Yes, that's perfect.
Very good. All right. So, in the last two lectures, I took you on a journey through how you would try to extend gravity, and I emphasized two key points, I think, which are that when you try to extend gravity, you essentially add new degrees of freedom. And almost all attempts at modifying gravity, at extending gravity, involve adding new degrees of freedom. But more, that when you try to extend gravity, you introduce new forces. And these new forces, these new fifth forces, are really what you're going to look for when you try and test them. I pointed out that we have very good constraints on fifth forces, and asked the question, given these constraints on fifth forces, why bother? Why bother worrying about those on cosmological scales? And then I argued that there's this phenomenon, gravitational screening, which appears in many theories naturally, and which kind of protects you in certain regimes from seeing these fifth forces. And so you might have a theory where things just look normal in, for example, the solar system, but it may have an impact on cosmological scales. So let's move to cosmological scales. And now this part of the course comes closer to what you've been doing with my colleagues, large-scale structure, in its various aspects in the cosmic microwave background. So this is what I'm going to focus on now for this lecture and probably the next lecture. The idea is that how are we going to use cosmology to test for things? Well, until the 1960s, basically, cosmology was really only about the expansion of the universe. And let me do that cool thing with the spotlight. There we go. Here we go. Cosmology was all about this metric, right? The Friedman metric and the scale factor. And all you really did was try and constrain the scale factor. And let me just remind you what that means. Universe is homogeneous and isotropic. It satisfies the Einstein field equations, but if the universe is homogeneous and isotropic, it breaks down into two equations. I call this the Friedman equation. So this is 3a dot over a squared is driven by rho. And then the Raychaudhuri equation here, which is in some sense, the acceleration equation. And these two equations tell you how the scale factor evolve in time as a function of rho and p. And how do you test for this theory? Well, how do you study this model? You study this model basically by measuring distances. You either measure angular diameter distances or luminosity distances, okay? You measure the distances to objects using some distance indicator, and you measure their recession, their redshift, and you end up with a curve, which is your distance as a function of redshift, and from that you determine your Hubble rate as a function of time or redshift. Let me remind you that this a dot over a is exactly this h. Now, let's try and change this, and this isn't letting me change. Oh, come on, please. There we go. Now, so you could say, well, let's focus only on the expansion of the universe, and we're measuring distances, we're measuring the expansion. Can we use that in some way to test for extensions to gravity? Well, let's see where we go with this. Imagine that gravity is extended somehow, is modified somehow. And let me just write down the general equations of motion. In principle, they're going to take the form of a two tensor, and it's going to be function of the scale factor, so the metric is still homogeneous and isotropic, rho, the density, and the pressure, okay? And maybe something else. There may be extra fields involved here, okay? So these are my completely general equations of motion, okay? Now I can rewrite this in the following way. I can add G alpha beta, and I can subtract T alpha beta. So I can add the Einstein tensor and subtract 1 over m Planck squared, the stress energy tensor, to both sides of the equation. And so I add G alpha beta here, and I add G alpha beta here. And then I add and subtract T alpha beta and subtract T alpha beta on this side. And I end up with an equation that looks like this. It's just G alpha beta equals this. This is just the Einstein field equation, plus some new thing, which has these indices, alpha beta, okay? And now, because we're talking about the expansion of the universe, this 2 tensor, if I know, I'm talking about the expansion of the universe, so I'm assuming that we're looking at the homogeneous and isotropic situation. This thing, we know exactly how to parameterize it. If it's homogeneous and isotropic, there are no off-diagonal terms, and there are 2 free functions. Let me call x sub e and y sub e, okay? But this looks exactly like what the energy momentum tensor of some fluid with some pressure looks like. In other words, suppose that you've got some modification, some weird modification of gravity. If you only look at the homogeneous and isotropic part, it's indistinguishable from if all we had done is add a fluid, a dark energy component, for example. So we won't be able to distinguish purely with the expansion of the universe whether the accelerated expansion or the deviations from LambdaCDM are due to some new fluid or due to some modifications to gravity. And because this is the data, basically, the data is you have some distance measurement, and let's not worry about what this is. It's just some distance, and you have some redshift, and you just have a curve, and that's all you'll be able to measure. So you'll never be able to distinguish with the expansion whether there's some modification to gravity or extension to gravity, or it's just a different fluid, some exotic fluid, okay, like dark energy. So what do we do? Well, we go to the heart of what this whole school is about, which is we look at perturbations. And so let me just remind you what perturbations are. You're doing this in the other lectures, so this is going to be short. We assume that the universe is inhomogeneous. That means that if we take the energy density of the universe, it has a homogeneous part, which is what drives the expansion, and then has fluctuations around that inhomogeneous part. That delta is nothing more than the energy density minus the mean energy density divided by the mean energy density, okay? And it's inhomogeneous. You look at the energy density and it'll have peaks and it'll have troughs. The peaks will correspond to clusters, walls or filaments. The voids will, the troughs will correspond to voids, okay? You can take the fluctuations, these fluctuations, and you can Fourier transform them. And then you know that the mean of this Fourier transform is 0 because these are fluctuations around the mean energy density. You can calculate the power spectrum. So you take the expectation value of the product of the two and you get a power spectrum. And the power spectrum looks something like this. This is a linear log scale, log P of K, log K. And on large scales, it goes up and it's approximately scale invariant, and then there's a turnover and then it decays. And I'm assuming that you're learning all of this in your lectures with Fabian, Dragan, Valerie, and others, and Yassine, all right? So this is what I want to focus on. I want to use this data, this information to constrain gravity. Now, I'm going to focus on linear theory, and I'm going to focus on linear theory, which is most of what you've learned, I guess, in these lectures, because it's easy to calculate, and also it is the success of modern cosmology. Much of the success at getting precise measurements and constraints from cosmology over the last 2 decades have been to do with being able to do this in the linear regime and calculating the linear regime really well. Now, the linear regime is what happens on very large scales, But we know that on very large scales, we're statistically limited. The larger scales we look at, the fewer independent modes we have to measure. And one way of thinking about this is if you have some kind of finite volume, okay, the number of modes that you can constrain will be proportional of a certain wavelength, will be proportional to the volume over that wavelength cubed. In other words, it's proportional to k cubed, which is k is the wave number. So the smaller the lambda, the bigger the k, the more statistically significant you are. But the larger the k, the smaller the scales, the more you have to worry about nonlinearities. So the downside of the linear regime is you have limited statistical power. But let's just go with the linear regime. What do you do in linear perturbation theory? Well, you expand your parameter, your fields, the quantities you're interested in linearly. So you've got your density, you expand it in terms of fluctuations around the background density. Your pressure, you expand your pressure as fluctuations around the background pressure. You take your metric and you expand it as fluctuations around the background metric, which is nothing more than the Friedman metric. And so you've probably had discussions about how you parameterize this. But for the purpose of what I'm doing here, I'm going to say basically the scalar part of this is characterized in terms of two potentials. Let's call these the Newtonian potentials. What you then get is you get the Einstein equations and you linearize them and you equate the linear part of this to the linear part, and you'll end up with a bunch of equations, which will look something like this. For example, Laplacian of psi will be equal to 4 pi g a squared rho delta plus some stuff. So this looks like a modified or a relativistic Newton-Poisson equation, the relativistic equation of the Newton-Poisson equation that you would do in Newtonian theory. You also get from another bit of the energy moment of the field equations that phi and psi are basically equal to each other, except if you have some kind of shear or some kind of an anisotropic stress. I'm not going to go into details. The point is, this is the kind of thing that you do. You have to solve some linear equations to figure out what perturbations are doing on the largest scale. Now, how can you go beyond general relativity? And the beauty of linear perturbation theory is they're linear. In other words, if the equations of motion are linear, then the action for the perturbations must be quadratic, right? If you've got linear equations of motion, if you want to find out what the action is, it has to be quadratic. And so what you do, as I said, you've linearized your metric and your other variables. Remember what I said, that extending GR normally involves introducing an extra degree of freedom. Let's consider extending it by adding a scalar degree of freedom. So in scalar tensor theories, you've got a scalar field, you have the background, and then you have fluctuations. And then all you need to do is look at the quadratic action. And this is what the quadratic action looks like for example, Hondesky theory. And I don't want you to look at it in detail. All I want you to look at is the following. It's basically, you have your different variables. Here's one of your Newtonian potentials. Here's your Newtonian potential times psi dot the other Newtonian potential. Here, the Newtonian potentials. Here's you've got fluctuations in the scalar field here, fluctuations in the scalar field here, fluctuations in the scalar field here. Okay, this is your action. And these bits, these bits are multiplied by time-dependent bits. There's h here, which is a function of time. And then you have these functions that I wrote in red. These alpha k, alpha b, these are functions of time. And these are basically come down from your scalar tensor theory, okay? In other words, if you look at this, what you find is that your general action for linear perturbation theory for scalar tensor theories is completely characterized in terms of these functions in red. And it turns out that we have, how many functions in red do we have? I haven't, turns out that you've got, I should have put this as red. This is the time-dependent Planck mass, which is one of the other things that comes up. You have 4 functions that you have to characterize. In other words, the most general scalar tensor theory can be described on cosmological scales. Perturbations can be described in terms of 4 free functions of time: alpha m, alpha b, alpha k, and alpha t. And these all have a particular meaning, and I suggest that you look at this paper down here to see what they mean. But for the point of what I'm saying, it doesn't matter. The most general scalar tensor theory on linear scales is characterized in terms of these four functions of time and, of course, the equation of state. Okay, and the key point to understand is that for general relativity, in other words, if you want to take the general relativistic limit of scalar tensor theories, you set all these alphas equal to 0. Okay, so now we've distilled this into, we've rephrased the problem as the following. We want to test extensions of gravity on large scales, on linear scales. What does that mean? What that means is that we want to measure these functions of time, alpha m, alpha b, alpha k, and alpha t, using measurements of large-scale structure on large scales. Okay. In other words, we work out, for example, what the power spectrum is of structure formation, and it'll depend on these parameters. And we fit this power spectrum, and it'll tell you the value of these parameters. Okay. So let me rephrase, let me just emphasize this. Constraining new physics on cosmological scales means measuring these free functions, the equation of state and these alphas. Now, this raises a number of questions. First of all, I'm just saying that these functions, the equation of state and these alphas, are free functions of time. But what functional forms do they take? That's the first thing. The second thing is, I'm saying that there are these 4 or 5 free functions, but are they correlated? Is there one free function and these functions come from it? And what range of values can they take? So these are all open questions that if I just gave you this and told you to go away and look for these alpha and measure these alpha b's, you could do that, but you need more information. You need to figure out what functional forms they can have and are they correlated and what values can they take. And this is an example of what happens when you try to do this. This is work being done by a graduate student at Oxford. And so she's looking at shift symmetric scalar tensor theories. Now, if you remember, when I introduced Hondesky theory, I introduced Galilean theories as well. And in the Galilean theories, we had this symmetry. They were symmetric under, you take your scalar field, you add a constant, and then you add another bit, which is a bit which is the dot product between some full vector and the coordinate x mu. Now, let's get rid of that last bit. So shift symmetric theories are theories which are invariant if you basically add a constant to the scalar field. Okay, well, if you do that and try and figure out what the equations of state does and what the alphas do, what you find is almost all the alphas are 0 except alpha b, which is one of the 4 alphas, and that alpha b typically obeys a functional form like this, where this and this is a free number. Okay, the equation of state also can roughly be approximated by some constant plus some variation as a function of a. Now, what I'm showing here is it fits some models pretty well. Other models it doesn't fit so well. It turns out that it fits them well enough if you only want to worry about observables. But the point being that when you start looking at specific theories, you start realizing that these alpha b's and these w's aren't completely free. You can pick restricted forms for their time evolution before you study them. Okay. Now, so this is the general statement. You take your general scalar tensor theory, and this is what the action for linear perturbations look like. All right. But you might want to restrict yourself and say, well, I'm not going to look on the very largest scales. Okay. When we try to observe the universe, we don't really observe modes which are close to the horizon. We typically are doing surveys which probe the universe on scales of hundreds of megaparsecs, but not thousands of megaparsecs. Okay. And it turns out that in that regime, and I've done a cartoon here of the logarithm of the power spectrum, so which is more or less this regime. So not the nonlinear regime, but not the very large scale. The equations simplify even further. In that case, it turns out that if you look at your extra degree of freedom, I've called it psi here, you can discard most of the time derivatives, and you can actually solve for delta phi in most of the equations. And then the evolution equations for the metric perturbations simplify dramatically. It turns out that all you need are 2 equations. It's the Newton-Poisson equation, which I've written here. So nabla squared phi equals 4 pi g a squared rho bar delta. So this is just delta rho. And then you have a mu here. And that's essentially the effect of Newton's constant, how Newton's constant is changed. And the other thing you find is that your two potentials are related by something which is called the gravitational slip. So we went from 4 functions of time to 2 functions. Now these are to be strictly speaking, these are functions of space and time, but actually it's good enough to just describe them as 2 functions of time. So the equations have simplified dramatically, and we've reduced the functions to the constraint to simply 2 functions, mu and gamma. Okay, so this is what is known as the quasi-static approximation and has been used a lot over the last decade or so. Now, how does this impact on observables? And I'm going to focus on one observable, which you may have come across in the other lectures. I'm going to focus on the growth rate. Okay. Let's look at the the conservation of mass equation and the Euler equation. This delta is the density perturbation. This theta is nothing more than the divergence of the velocity. The conservation of energy equation, the linearized conservation of mass equation or energy equation looks like this. The Euler equation, the conservation of momentum equation looks like this. Okay, and we know how to work with this. We can convert these 2 equations into one second-order equation for the density perturbations. Okay, that's the first thing. The other thing is we can transform this from a derivative with regards to time to a derivative with regards to the logarithm of the scale factor. And if you do those 2 things, you end up with a second-order differential equation that looks like this. Okay, but you can go even further. You can define a quantity which is called the growth rate, which is the logarithmic derivative of delta by log A. Okay. And then if you do that, this equation becomes even simpler and looks like this, okay? You get an f prime plus some function times f plus f squared plus 3/2 omega m, which is the fractional energy density and mass, times this psi. And this psi is nothing more this mu over gamma, okay? So the first thing to note is there's an explicit dependence on how these deviations from general relativity enter into the growth rate. If you have deviations from general relativity, it's going to affect your growth rate. The second thing is there's this function here, and this is simply depends on the equation of state of the background. And all this is saying is that the growth rate will also be affected by the way that your universe is expanding. So if you affect the expansion rate, it will affect the growth rate. So immediately you can see that if you can measure the growth rate, you can measure not only modifications to gravity, but you can also measure the expansion. And there are going to be degeneracies between the 2. This is a plot of the growth rate. And there are interesting things to note about the growth rate, this f that I had there. If you have an omega m equals 1 GR universe, that f equals 1. So it just should be just a straight line. If you have LambdaCDM, it goes as omega m to the 6th 11th. That's a beautiful approximation. And so this is exactly that curve. And so you would be looking at deviations of the growth rate from that curve. So that's one way of observing, one way of trying to look for these parameters. Okay. The other way to try and look for these parameters is by looking at weak lensing. And my guess is that you will be looking at weak lensing. My guess is that you will be looking at weak lensing in some of the other lectures. So roughly, weak lensing, if you remember, you look at distant galaxies, and the light coming from distant galaxies will be deformed as it passes through intervening space-time because of deformations in the metric. What this means is that you'll introduce correlations between the ellipticities of distant galaxies. And so if you can measure these ellipticities and correlate them, you can extract information about the intervening potentials. These are the intervening potentials, and this is, in some sense, the kernel, how much the potentials at a given redshift affects things. Now, the equation looks a bit like this. You have to take the Hessian of the sum of the potentials. But now let's use those equations that I gave you, which are valid when you extend gravity. First of all, you can rephrase psi in terms of phi by putting 1 over gamma here. And then you remember that you can rephrase phi by using the Newton-Poisson equation. So you put a mu here and you bundle up all that stuff over there. And what you end up with is this combination of those parameters, the sigma parameter, which is over here. So often people talking about constraining mu and sigma or mu gamma and sigma. All of these are constrainable by observations. So let me summarize this kind of introduction to this part, which is we can use cosmology to look for new physics. And background evolution, cosmology begins with background evolution, so the expansion of the universe, and there's too little information there. So we use large-scale structure. Now, linear theory is very well understood, but statistically limited. We have a general parameterization of new physics, which is, for example, for scalar tensor theory, it's those alpha parameters. If you look on quasi-static scale, it's the mu and gamma. And then we look at how what we really want to do is we want to see how these things impact on observables. And I mentioned two. I mentioned the growth rate and weak lensing. So I'm going to pause here and stop sharing. Hang on. Yes, stop sharing and see if you want to ask me any questions. Let me go to the chat. I've got 6 questions in the chat. Hello, could you please clarify me the line of thinking that leads you from the middle K, not too small and not too large, to the quasi-static approach? I got both explanations, but I didn't get the connections between them. Let me try and understand the question. Do you mean why is the quasi-static approximation in that, around that value of K, around those values of K? Is that what you're asking? I think you need to either answer in the chat or turn on your...
Yes.
Okay.
Yes, please.
All right. Do you remember when you do general relativity, right? And you do the Newtonian approximation. What you do is there's a key aspect of when you do the Newtonian approximation is you consider the kind of non-relativistic limit to some extent, which really what that means is that you get rid of time derivatives of the gravitational potential, okay? In other words, spatial variations are more important than time variations. And when you do that, you get rid of a lot of a lot of terms and you end up with a Newton-Poisson equation. The quasi-static approximation, and in here, static is the key thing, is exactly the same thing. If you look on sufficiently small scales, the gradients are sufficiently large compared to the time derivatives that you can discard the time derivatives. And you end up with, in some sense, static equations for the scalar field, which you can solve for and replace the scalar field wherever you have it. Now, this is an explanation why you look on smaller scales. So this explains why you limited this for small k's. Remember, small k's is large scales. So that explains one side. The other side is we want to do linear theory, and we know that on smaller and smaller scales, you enter the nonlinear regime. So on the one hand, you're limited by the validity of the quasi-static approximation. On the other hand, you're limited by wanting to be in the linear regime. Okay, the questions are going a bit too fast, and I think I've lost some already. What does the growth rate physically measure? Very good question. The growth rate measures how quickly stuff is collapsing. So imagine you have a galaxy which is forming. It tells you how quickly that galaxy is forming, or a cluster. So if the growth rate is larger, it'll collapse more quickly than if the growth rate is smaller. Okay, how did you construct the quadratic action for perturbation theory? Is it by using effective field theory? You can use effective field theory, but actually it's much simpler. What you do is you get your most general scalar tensor. So the question is, how do you construct the quadratic action for perturbation theory? I did it for scalar tensor theory. Remember that I wrote down the Hondesky action. What you do is you take your Hondesky action and then you perturb all your variables around the Friedman background, and you only keep the quadratic terms, okay? You throw away all the others, and then you reorganize everything, and you'll get your quadratic action. G naught is the standard Newton constant. How can we measure GF? So G naught in what I wrote is really kind of the bare G Newton, the G that goes into the action. How can we measure G effective? Well, as I showed you, on large scales, we might measure G effective by measuring the growth rate. As you see, G effective is given by mu, and mu enters the equation for the growth rate. If sigma is in function of mu, why people are trying to constrain Hondesky theories you both like if they was independent? Well, no, it's a function of mu and the slip, okay? Remember that we had two functions, mu and gamma. The growth rate, the way that I've written it, constrains mu and gamma. The weak lensing constrains mu times 1 plus 1 over gamma, right? So these are different combinations, and they're different combinations which are linearly independent. So if you constrain these two things, you'll constrain mu and gamma. Can you talk about testing GR combining weak lensing with intrinsic alignments of galaxies? I'm really sorry, I can't. I don't have time for that. Hi, Professor. Can you make briefly describing the effects of alpha M running mass and alpha K kineticity to the CMB temperature multipoles and structure formation? I'm sorry, I can't. That's we'll see a little bit of that when I talk about Jordan Brans-Dickey, but that's quite detailed. Is there some way to look for modifications of general relativity that doesn't depend on the model of modified gravity? Well, this approach of writing down a general action on large scales, you always have to make some assumptions. You have to assume, for example, whether your extra degree of freedom is a spin 0 field, is a spin 1 and spin 2, and you can look at my papers, I've done that, but you always have to make some assumptions. So you can broaden and broaden and broaden your scope of what you're doing, but you always have to make some assumptions. GR is a highly nonlinear theory. What do you mean by the linear theory? I mean that we look at the Friedman universe and we linearize perturbation. We look at linear perturbations. This is exactly, I think, what you've been doing over the last week in the other lecture courses. You have your background spacetime and you look at linear perturbations around that spacetime. Our effective field theory, no, this is just linear perturbation theory. This is classic linear perturbation theory. What are the probes of large-scale structure used to constrain alpha X? Are you accounting for the bias between the matter field and the galaxy? This is a very good question, and we will get to that in the next part of my lecture and on tomorrow. So if sigma is in function of mu, why people are trying to constrain Hondesky? I've already answered that question. I think you're just repeating the question you asked above. Okay, I think we are ready to move on. Okay, let's do this again. And then I go here. So now I'm going to enter quite an extended part, which will probably be partly today and partly tomorrow, which is how do we use data to constrain? Okay, and so this is quite a complete look at this. And let me just have a drink. This is going to be a marathon. So, one of the surprising things about this field of beyond LambdaCDM is theoretically, it's not necessarily part of the mainstream of research that people are looking at. You know, there are quite a lot of people doing this, but it's not part of the mainstream. Yet, testing gravity is one of the primary drivers of future cosmological surveys. If you look at the science cases for SKA, Euclid, the Rubin Observatory, the Roman Observatory, they have written in that one of the key things is testing gravity. And it's already an integral part of current analysis of other surveys that you may have heard of. BOSS, EBOSS, KIDS, DES, Viking Viper, any number of them. And so it is interesting that the observers have really taken on board the interest of trying to look for deviations with their data sets. And let me just remind you what are the key observables, okay? So I mentioned that you have distances. And by distances, it can be luminosity distances, angular diameter distances. And what you do there is you're basically measuring the Hubble rate as a function of redshift. And this lets you pin down the equation of state, okay? Remember how you've probably learned how H of Z can be is given in terms of various fractional energy densities. and the equation of state of whatever you're considering to be your dark energy. Then you've got the growth rate, which I mentioned. And let me remind you what I wrote. I have the growth rate. Look, is an equation that looks like this. This is solely due to modified gravity. This is 1 if there's no deviations from gravity. And this is due to the changes to the expansion rate. And then you have lensing, okay? And lensing, you have this parameter sigma, okay? And so what do you want to constrain? So these are the observables. And what do you want to constrain? Well, you obviously want to constrain the equation of state. You want to constrain, if you're looking at scalar tensor theories, you want to constrain these parameters, these alphas. If you decide that your data is mostly in the quasi-static regime, you can constrain your gamma and nu. And you can worry about how do these things depend on time. So a parameterization of the equation of states that is often used, and the more I use it, the more I'm convinced it's a really good parameterization, is this. It's almost like a Taylor expansion around today. You have a mean bit, and then you have a bit that depends linearly on the scale factor. Okay, when a equals 1, that's today. The alphas, often people have used this parameterization where you say that alpha is in some way correlated with the energy density of dark energy. So well back in the past, when the fractional energy density in dark energy was almost 0, this is almost 0. And but as this becomes important, this becomes important. And you can understand the motivation behind this. The motivation behind this is that if you are assuming, you're trying to assume that there are extensions to general relativity that lead to the dark energy. They're correlated somehow. And this is enacting that correlation. You could be much more extreme. You could say that your deviations have existed for all time, so they're just a constant. And this is very extreme, but possible. Or you can do something even simpler. You can say, well, I'm going to be completely agnostic about this, and I'm going to divide up the history of the universe in bins, in redshift bins, and assign a value to my alphas in each of these bins. So there's a value from today till redshift of 0.1, then there's another value from redshift of 0.1 to 0.3, and this is kind of the most general and uninformative way of doing it. And let me just show you what that means. This is what I meant when in the case of bins, I've got my alpha, this is redshift, and I say I measure a value of alpha here from out to redshift 0.1, then from between 0.1 and to 0.2, 0.2, 0.3, all the way back, okay? You can even go further. You can say this alpha is also scale dependent. And if this alpha is scale dependent, you would have, it would depend not only on redshift, but also on scale. And the more you do this, the worse your constraints are going to be. And there really isn't any motivation for considering scale dependent constraints on the alpha. Now, I'm just going to continue hammering on about this parameterization because these parameters are crucial when you're trying to constrain gravity. Something to realize is that results depend on the parameterization. And you can ask yourself the question, is there a physically motivated choice for the time dependence? In other words, are there physical priors? And later on, I will show you an attempt at trying to answer this question. But the results do depend on the parameterization, okay? Let me just remind you what the quasi-static approach is. That was for the alphas. For the quasi-static, we look at the modified Newton-Poisson equation. We've got the mu, we've got the gamma, and we've got the weak lensing parameter here. And I explained to you, I showed you, I've already explained this to you in my about 10 or 15 minutes ago. And right, so these are the parameters. So here's your first data, okay? This is using the Planck analysis, the Planck data set. This is a measurement of the cosmic microwave background, which you learnt with Yassine. And it's a constraint from that. And on the x-axis, you have one of the parameters -1, and on the y-axis, you have this here. And what you find, which is really interesting, is if you take the Planck data and you combine it with other data sets, weak lensing is weak lensing. These are the baryon acoustic oscillations. You've got redshift phase distortions. Look at what you find. You find a marginal deviation, well, more than 2 sigma deviation from what you expect from general relativity. So general relativity is over here. And what it seems like is that the 2015 data is actually inconsistent with general relativity. Okay. Now, this is the 2018 data. And this is very interesting. And I recommend you read the review that I've advertised on these on at the front of this particular set of transparencies. This is the 2018 data, and they found a number of things. But the most important thing that they found was that if you include lensing, in other words, when you measure the cosmic microwave background, not only do you measure the background anisotropies, you also measure the lensed anisotropies. You push it towards it being consistent, and that there is actually an inconsistency within the Planck data itself, which was pushing it away. And this inconsistency is the fact that when you look at the cosmic microwave background, the anisotropies, you're not only measuring the oscillations in the cosmic microwave background due to the primordial fluctuations, you're also seeing those oscillations deformed by lensing from the intervening space-time. And this will squash the peaks. This will smooth out the peaks and smooth out the troughs, and will slightly modify things. Now, we think we know how to model this lensing, but what's happening is when we try to do that in the context of LambdaCDM, we seem to be off by a few sigma. And that few sigma is then converted into this few sigma deviation here. So this kind of detection of modification of general relativity at the moment is nothing more than an unexplained inconsistency in the primary Planck data set itself. Okay, so that's the first interesting thing you find. Okay, now here's another interesting thing. This is constraints from weak lensing and the Planck data. On here, you have sigma 8, which I believe Dragon is explaining to you at the moment. And here you have the matter density. And here you have the constraint from the Planck data. All right. And over here, you have the constraint from a particular weak lensing survey, the KIDS survey. And what you find is that they are statistically, consistent, but they're a little bit off from each other. There is this mild inconsistency. Okay. And again, this is the reason that this is happening. This is because the lensing is smoothing out the peaks in the angular power spectrum. And so it's pushing this up here when it should be further down there. So this is a kind of a fundamental, unexplained phenomena in the Planck data. And here I'm just showing you what this means. Again, the same thing. This AL is the amplitude of this lensing effect on the cosmic microwave background. And you can measure this thing from the Planck data, and you would expect it to be peaked at 1 for LambdaCDM, and it's off. And you can see that it's off. If you look at this blue line, it's off by quite a bit. All right. So we still don't understand what's going on here. And anyway, I'm not going to look at this. One of the interesting things is this then translates into, do I need these transparencies? I mean, I could go into this. This is interesting because this just shows how this lensing is correlated with that S8, that sigma 8 deviation here. What this shows is that if you let AL go bigger, this S8 goes down, sorry. What shows is that there's this correlation between your S8 and your AL, and that by varying AL, you can actually make the Planck data. And sorry, I've got confused here. What this shows is that if you let this AL vary, if you fix it at 1, it's quite high. But if you let this AL vary, which we don't understand, this comes down, which means that this would come down and be consistent here. Okay. So all this is pointing, the only reason I'm going through this is just to point out why there is this inconsistency, because there is something in the Planck data which we don't understand yet. Okay. Now, here's an attempt at using the weak lensing to constrain by itself it's the attempt by the weak lensing to constrain mu and sigma. And so this all that matters is that this is mu for all intents and purposes. This is mu, and this is sigma, okay? And what you find is that weak lensing, mu is completely unconstrained by weak lensing, but it is constrained, but sigma is constrained by lensing. And that's not surprising. Remember what I told you. Weak lensing depends on sigma, right? This parameter, where is it? Where is it? I'm sorry, let me find it. There it is. This sigma is the weak lensing parameter. Remember that I showed you where it came from. So weak lensing is indeed doing what we expect it to do. It's constraining sigma. I mean, the constraints aren't great, right? This goes from 0 to 2. These are what, of order 20%, 30%, around 1. It has absolutely no constraining power on mu. The difference between these two, if I'm not mistaken, is how far you go into the nonlinear, how much of the linear modes you include. Okay, and what you show is that if you want to be conservative and you don't include too many modes, the error bars are huge. Okay. Now, these are the equivalent DES constraints, and where you want to look at is over here. And what do you find? You find quite large uncertainties. So this is 10 times sigma, all right? So when you look at here, you're really looking at 0.5, all right? And so what you're finding is that the DES constraints, first of all, are degenerate with S8, but with sigma 8 times that power of omega. And you have constraints on mu naught over here, all right? So this is the current state-of-the-art constraints on the growth rate and the lensing parameter, okay? This is an interesting plot, okay? And so this was a good, useful exercise because I was able to go through all the different attempts at constraining these deviations from gravity. So I think until now, what am I saying? What I'm saying is you're getting constraints of, I wouldn't say of order 1, but just below order 1 with current large scale structure and lensing data. So that's where we are. This is what happens when you start messing around with the time dependence. This is a constraint on that, what I called psi, mu over sigma, with the BOSS data, okay? And here what they've done is they've parameterized it by a constant plus something depends on a to some power s. And that s, you can make it equal to 0, to 1, or 3, okay? And what do you find? If you have s equals to 0, in other words, this thing is a constant, okay? If this thing is a constant, what you find is pretty tight constraints, okay? You find, well, reasonably tight constraints. You find constraints of order 10% on this quantity here. But if you start changing the time dependence, the uncertainties get larger and larger. So it's clear that it's crucial to know what is the time dependence, or have some idea of what is the time dependence, what is the sensible time dependence that we should assume for these parameters. This is an attempt at constraining the alphas themselves instead of the quasi-static approximation, just going for the alphas themselves, okay? And so here, how have they parameterized themselves? You've got your alphas here, and they've parameterized them that way that I said. So you have a constant here, the CX's, times the energy, the dark energy and fractional energy density. And let's just remember that GR is when this is equal to 0, okay? So we're actually going to look on this plot at C's, okay? And so you have CB here, CM, and CT. It turns out that alpha K is completely unconstrained by cosmological data. It doesn't enter on those scales, okay? So these are the only 3 things you can constrain, all right? And what do you see? Well, you see that you've got uncertainties of order 100% in CT. But again, one of the interesting things that you find is CB. Look at what's happening with CB. The contours pinch off before 0. They don't encompass 0. And remember, 0 is what you get for general relativity. And again, the reason this is happening is exactly the same reason that we were getting that detection in the Planck data. There is something not understood in the Planck data due to weak lensing. So I think I'm going to end here for today. So this is kind of an almost a summary of where we are in terms of constraints with with existing data. Let me just quickly recap. Oh no, actually, I'm going to stop here. I'm going to stop here because I think this is quite a big part of what I want to talk about next, and I'll do this tomorrow. Very good. I'm going to stop sharing, and I'm going to use the next 5 to 10 minutes to answer questions.
Okay, so you can write questions in the chat, or you can raise your hands. I can start asking a question about the alpha parameters. So when you say, so the alpha parameter, sorry?
Just 1 second. Just 1 second. I have a problem with the chat, which is if people ask too many questions, the questions go up and I lose the earlier questions. And I have no way of recovering those questions. Do you know how to recover them?
Yeah, just roll down.
Oh, I just scroll. It's easy. Good. All right. All right. That's fine. Ask the question.
So my question is about the quasi-static approximation. So did you say that when you use the alpha parameters, you don't need to use the quasi-static approximation?
When you use the alpha parameters, you don't need to use the quasi-static approximation. No, it's general on all scales, sub-horizon, super-horizon.
Okay, and what is the code that is used to generate the power spectrum with those alpha parameters?
It's called high class. You can also, there are two codes. It's either high class or EFT CAM. Let me write it in the chat.
Thank you.
There we go. Very good. Okay, what does sigma 8 physically measure? Very good question. I think Dragan is talking about that now.
Yes, I already said Dragan has a whole lecture on that.
All right. What is the motivation for WZ equal? How is it justified? Well, it's as you say, it's kind of a Taylor expansion around A equals 1, but it's really quite a good. I mean, if you think about it, it's the simplest thing you could do, right? It's the simplest thing you could do to fit an equation of state when it matters is close by. Why does it stop at first order? Well, if you think about it, you're really only going to measure the equation of state close to redshift 0, because further back in time, the dark energy is subdominant, so you'll never be able to constrain it then. So it's only worthwhile. You'll never be able to really measure the next order terms. Exactly. All right. How can we constrain alpha m using screening in Hondesky theories? So alpha m is something that manifests itself on linear scales. Screening is a non-linear phenomenon. Now, it may be possible to infer something about alpha m from constraints on screening, but I don't have a straight answer for you because it's a non-trivial connection. Okay. Now, Rafael asks, could these inconsistencies in the Planck data be related to the disagreement of values for H0? Very interesting question. If I had time, or if I could find it, I would show you a plot, which is a correlation. But if you look at the Planck paper, there is a correlation between alpha L and H0, and there is a correlation. It may not be enough, but there is definitely a correlation. So I think that might have something to do with it. If you use the best fit values for the alpha parameters from the Planck data, can you reduce the H0 tension? There are attempts at doing that, but if you think about it, the alpha parameters affect the fluctuations, and most of the H0 tension comes from measurements of angular diameter distances and luminosity distances, which really only depend on the equation of state. I have a question about the degeneracy between AL and S8. Is it expected by most, do you think, that the difference between S8 from Planck and S8 from kids is due to an issue with lessening? I think a lot of us believe it is. I mean, I still think there is something that has to be explained about the Planck data, which is this problem with AL. What is the physical interpretation of the gravitational slip? Super interesting question. I think I mean, there are explanations which don't satisfy me, which is, well, it's the difference between phi and psi, between the time potential and the spatial potential. But it turns out that the gravitational slip maps onto, on small scales, something that some of you are familiar with, which is the Eddington parameter. okay? And the Eddington parameter is something that you can constrain quite well with certain observations, typically to do with timing, well, typically to do with timing. So if you want to go and look for an interpretation that understands you, I would push you in that direction. Try and understand. Go and look at the gamma ppn parameter, also known as the Eddington. Well, I think it's the Eddington parameter, and see what that means. Can Euclid data solve this problem of Planck data, since we will have more precise constraints on WL growth rate and W? Well, the Euclid data could only solve this problem with the Planck data if the Euclid data came back with a constraint which was different from the one that's being obtained by KIDS and DES as well. But only CMB measurements would be able to solve the problem of Planck data. And I don't think it is a problem with the Planck data. I think there's something that we just don't understand about the signal. I don't believe it's a instrumental systematic. I think there's something. I think we're measuring something and we're misinterpreting it as lensing.
I don't.
Let me look at the Slack. Let me look at the Slack.
I don't see more questions.
Okay. Well, I can have lunch.
I have one further question, if you don't mind, since we have time. 2 minutes. So I noticed that for the Galilean theories, that you showed a plot where the equation of state looks mostly less than -1. Is there an explanation for that?
Why in Galilean? Sorry, this is my doorbell ringing. I can't go. Why is there? You mean? Oh, I see. When I showed you the shift symmetric curve, is that what you mean?
Yes, yes. You showed the equation of state for the Galilean theories.
Well, I think it's. Let me try and find it, and so we can look at it together.
I think it's one of the plots of your student in Oxford.
Yes. Look, I think it's a non-minimally coupled theory, and so when it's a non-minimally coupled theory, all bets are off, right? I mean, you know that, right? I mean, it's not a minimally coupled quintessence. You know, it's not a minimally coupled field. So, I think that's why. And it's. Can you see it?
Yes.
You can see, right. Yeah. It's not full screen, but I think it's good enough, right?
Yeah.
And so we're talking about this bit, right? I think it's simply to do with the fact that it's non-minimal coupling. The Galilean has that box phi times stuff, right? And that non-minimal coupling just changes everything.
Okay, thanks.
That's the way to answer that. I think that's the fairest way to answer that.
Okay. So Zakaria has another question.
I've already answered.
Go ahead.
It's just a last question. I'm wondering about theories beyond Hondesky. So can we do the same thing and use these parameters for those theories and constrain them? Because I know that it was done with gravitational wave to constrain one of the parameters. But what about the other parameters?
Yeah, so you actually, beyond Hondesky, there's a class of theories called beyond Hondesky, where you can extend it, and there's these alpha H parameter. You add in one new parameter for the beyond Hondesky, and I don't think this exercise has been done for the dosed theories. And I'd be curious to know if these parameters would be degenerate with these parameters, if all you get is a rescaling of the existing parameters, or if you'd actually genuinely get new terms in the perturbation theory, in the quadratic action.
Okay, so I don't see any other questions, and it's the hour now. Pedro has to go. So thank you very much, Pedro. And he'll not be, as I said in the beginning, he's not going to be able to participate in Q&A this afternoon, but he'll be in the Q&A tomorrow, and there'll be time for more questions during his last lecture. So thank you very much, Pedro. And I see you all in half an hour for Chiara's lecture on gravitational waves.